Ejection seats were first created in the 1920s and were perfected around the World War II time, and they drastically increased the safety for pilots and passengers of aircraft when they were crashing. And these ejection seats, while they increase the safety, they also have an extreme amount of physics involved with them, mostly dealing with force and acceleration. One equation that can be used to solve for the acceleration of ejection seat would be Newton's equation, which said that force equals mass times acceleration. And because of the extreme amount of force put on a pilot when he is ejected, and the mass, which would probably be an average of about 140 pounds, then the acceleration is also going to be massive as well. And another way to find out the acceleration is using the equation of velocity final, or equals acceleration of time plus velocity initial. And when we solve for acceleration, we get acceleration equals velocity final minus velocity initial over time. And because the time is going to be such a short amount, when you subtract the two velocities and make it divided by a very small amount, you're going to get an extremely large acceleration. And when someone gets ejected from an aircraft, their typical acceleration is in the 5g to the 20g range. And 1g of acceleration is equal to the gravity, which is 32 feet per second squared, or 9.81 meters per second squared. So the typical g is normally 12 to 14. The typical acceleration is around 12 to 14 g, but depending on the aircraft, it's anywhere from 5 to 20 g. And the average would be about 117 to 137 meters per second squared for their acceleration out of the plane, which is pretty high.
Very popular today in America. This is due to their large acceleration and fierce drops. When dealing with roller coasters, there are two different types of acceleration: chain acceleration and launch acceleration. We'll be focusing on chain acceleration today. Roller coasters work because of its conversion of potential energy to kinetic energy. This is really what drives the roller coaster. The energy that you need comes from the first hill. When you move up the hill, you are gaining more and more potential energy. This potential energy is then converted to kinetic energy once you move down the hill. The roller coaster is brought down by gravity because it is almost a free fall, and it is gravity which is pulling the roller coaster down. This acceleration is due to gravity, which is 9.81 meters per square second. And this acceleration occurs towards the center of the Earth. The initial hill, or the lift hill, is the tallest of the entire ride. As it is pulled to the top, it is gaining more and more potential energy. This energy becomes stored. The higher the lift, the greater the amount of potential energy used by the train. This is shown by the equation for potential energy. U sub G equals mgh. Ug is potential energy, while N is mass in kilograms, G is acceleration, gravity, 9.81 meters per square second, and H is the distance above ground in meters. Centrifugal acceleration is one of the main driving forces behind the roller coaster. This is also what gives the roller coaster its thrill. Centrifugal acceleration is not a true force, but rather the result of an object's inertia. This is also known as the resistance to a change in direction, usually when you are in a circular motion. The force points towards the center of the circle, but a roller coaster would feel centrifugal force pushing them toward the outer edge of the car. The following equation expresses centrifugal acceleration. A sub r equals velocity squared over r. AR is centrifugal acceleration, while v is velocity and r is the radius of the circular path. For example, if you have two roller coaster cars entering two loops of different sizes at the same speed, they will experience a different acceleration force. The car in the tighter loop will feel greater acceleration, while the car in the wider loop will feel less than acceleration.
Roller coaster rides have many changes in speed and direction and acceleration. And when a roller coaster changes speed, the rate of change of speed is the acceleration of the ride, which can be seen here. As you see, this is a typical velocity versus time graph, and as the time is right here and the velocity is increasing, the acceleration has this upward slope as represented by A1. Then when it reaches T sub 1, where it reaches the highest point of its velocity, which would be on a roller coaster, which would be at the very bottom of the hill, the first hill, you can see that the acceleration has that slope of 0. And then right after that, T sub 1, which would be right after the bottom of the first hill, you can see that the acceleration has this downward slope at A sub 3 because of what the derivative is. And then roller coasters also have many common misconceptions about acceleration and velocity. The first one would be that changing the height of a roller coaster will significantly increase the speed and acceleration, but changing the height of a roller coaster will actually not do anything to affect the acceleration. The acceleration would be more based on the angle of descent, and the closer the angle of descent would be to 90 degrees, the higher the acceleration would be, and it would be close to 9.81 meters per second because it would be close to a free fall at that angle. And actually with the velocity, the greater the drop height, the less initial velocity actually influences final velocity, and the speed is not directly proportional to the drop height, but to the square root of the drop height. So in order to double the speed of a roller coaster ride, you need to quadruple the height of it. So increasing the height has actually left kind of a minor effect on the speed unless you increase the height dramatically. Also, another one is that acceleration increases on a roller coaster with the weight of a rider, when actually the acceleration of a roller coaster is independent of its mass. So it doesn't matter how heavy the riders are or how heavy the car is, the acceleration is independent of that, and it's based on, like I said previously, the angle of descent.